Hi. We're going to split a list of words into those that have an even number of letters and those that have an odd number of letters. And the ordering is important. We want the odd ones first, then the even ones. I'm going to go through 3 different ways to do this, but there are many ways that this could be attacked. Here's some test data. So we have first some even words and some odd length words, and then some mixture after that. We can start by using tally to count the number of letters in each word. We're not actually interested in the real number of letters, we're just interested in whether it's odd or even, and an easy way to do this is to look at the remainder when dividing by 2. So this is the 2 remainder of these numbers, the length of each one. This means if you're dividing by 2 and the number is even, there's nothing left over, so you get a 0, and if it's odd, we get a 1 left over that we can't divide evenly into whole numbers. And this pattern we're going to use in all our solutions. This is the basics. Right. At this point, let's make a lambda or a defen that takes an argument outside of these braces and refer to the argument with omega. So this is the same. And then we want a pair. We want basically 2 masks. We want 1 mask for the odd numbers and 1 mask for the even numbers. So this mask that we have here, that is for the odd numbers. And if you want to get the even numbers, then we can do a Boolean negation, a not. That gives us this mask. So how can we get both masks? Well, we could use a variable and so for 1 mask and then compute the other mask based on that. But we can also be a little bit more clever. There is an operator, a higher order function called over, which allows us to take a function and apply it to 2 arguments, but pre-process both arguments first. This will allow us to concatenate the enclosures of 2 masks. So let's say that we have this mask over here and we use the commute or selfie operator to also place the mask on the left. That means we're concatenating the enclosure of this mask with itself. That gives us 2 identical masks. Of course, we don't want that. We want the original mask, as we have it here, and its negation, Boolean negation. So we can use the beside operator to pre-process the right argument to this derived function with the not. And this gives us the mask and its negation. Each one of these masks we then want to apply to the argument, which is the list of words. So applying it, we want actually to replicate. We want to, or also known as compress. We want 0 of the first word, 0 of the second word, 1 of the third word, and so on. And that's used to this slash. Now, we always want the data that's being replicated to be the right argument. So we bind the right argument as a fixed, constant right argument to this function, which would take 2 arguments, but now only takes 1 argument, which is the mask, which then conceptually goes on the left. But a 1 argument function, a monadic function, always takes its argument on the right. And we apply that to each one of these 2 masks. And that gives us a solution. There are many ways that the components we have here could be mixed and matched, but this is a very nice, straightforward flow solution. Let's call that F. Okay. In the specification for this problem, there's actually a hint saying that we could use the key operator. So let's try that. We start off the same way as before with the 2 remainder of the tally of each on the sample texts. And all we want to do here with the key, it groups things by a certain characteristic. So we want this characteristic, this being even or odd to be the keys, and the values that we are grouping is just the original data. So we could do it by putting parentheses around this, which becomes a little fork here. And then we use the key operator, and the data, the values goes on the right. And then we need to choose a function. And the function we want here is, we don't want to ignore the left argument and just enclose the data. So we want the enclosure of the right argument to that. And this almost solves the problem, but notice that the ordering is wrong. And ordering depends on the appearance of odd and even numbered words in the argument. And since the first word we encountered had an even number of letters, then the first group is the even number. So how can we force the ordering that we want? Well, there are a couple of different ways, and I think the simplest one is to just inject words that have the right length, and then we remove them afterwards because they're not actually part of the incoming data. So here, this identity function refers to the right argument. This whole thing actually is one big fork. This means we apply this function on the left and this function on the right, and then this function in between them, which is the grouping. So instead of having an identity function applied, we want a function that prepends an odd numbered word and an even numbered word. Now, the shortest odd numbered word would be a single character. It could be a right tag for that sake, but just a space is fine as well. And the shortest odd numbered word is a zero length word. So we bind those as left arguments, just like we were using bind before as for right argument to the replicate function. We're now using bind to bind a left argument to the catenate function. So this will prepend two words, so-called words, to the argument. And then similarly over here, we already know whether they are odd or even. The first one is odd, and the second one is even. So we can prepend that to our result. There's no reason to compute that over here. And that gives us the correct ordering. And this gives us all the odd ones first and then all the even ones. But there's one element too much for each one of them. So we can drop one from each. Now, because we only have a single function here, which is an argument bound to the concatenate, and we have a whole train here, this is a fork of a fork, then we need the parenthesis on the left side here. We can also move things around. We can swap the arguments of this middle tine function and then just move the outer functions around. And this will allow us to remove the parenthesis on the right, for those that prefer to do it like this. And we don't really need these spaces either. So this is another nice solution that we can apply. So there we go. And finally, something one might not think of at first, and that is to use grading, or we could say sorting by extension, to solve this problem. The idea is that we sort by the even oddness. That puts all the putting all the odd ones first and all the even ones at the end, and then the only thing that remains is to split the result into two at the right point, where we transition from odd ones to even ones. And so the way we can do that, let's create another lambda with the test cases over here, and we begin exactly the same way as before. The two remainder of each, of the length of each. This time, let's give that a name, so we can call that n. It's kind of like the number, whether it's a odd or even. And then we can sort by that. So let's start by sorting, and since we want the odd ones first, and the odd ones have the n equals 1, then we want to sort descending. So descending on n. So we can see that this puts all the odd numbered words first and all the even numbered words at the end. Now we can call this S. We want to know how many are there that are odd numbered. Well, since we get a 1 for every odd numbered word in the list of odd evens for all these words, that means that the total count of ones is just the sum of the mask. So we can find the count of odd numbered ones as the sum, that's the plus reduction of n, which is then going to, well, we can try it out first. There are 4 of those, so that's all odd, the, and great. And then, of course, there's going to be also 4. But we don't need to compute that because we can then use this. Let's call that C. We can now say the number C take of the sorted list, and we can do C drop of the sorted list to get the rest of them. So now we can make a 2-element vector, C take of S and C drop of S, and that gives us our result. This is very much broken up into tiny little steps. You can try to compress this a bit, combining things, and there are some cute ways that we can do this. Here we have C and S, and we have them in the same position, C on the left, S on the right, and then we are joining those two together, which means that it's kind of a fork, right? We have outer arguments here, and then the results are joined together, although we're not using an explicit function here, but we'll get back to that. Okay, so let's try to put things together here. If we have S, so this is our expression for S, we want that on the right, and then we want the expression for C on the left. Then all we need to do is have a fork in the middle. So we want the take and we want the drop, and then we need to have the concatenation of the enclosures. So that's that catenate over the enclosure of the two. So here's a partial putting everything together, but we can actually do better than that. The thing is that we need this enclosure, and we are computing this expression separately. If we put them both on the right instead, like this, then we can use, now we only want monetic functions, so we want this one applied and this one applied. And what we want applied is actually, we want an insertion here of a tick function, an insertion of a drop function. We can use the reduction for that. And it's so lucky that when we reduce from a vector, 2-element vector, then we must get a scalar, because we drop the rank down, reduce the rank. And we do that by enclosure. So that automatically encloses on both sides. We can write this fork like this. And now we can substitute in this expression for n in the rightmost occurrence. So this puts everything together with an inline assignment. However, we can also be a little bit more clever and make this a fork. So we can see the argument as one argument, and the group number, if you want, or the even odd number, as the other argument. So we can make that a fork all the way out here. So we say the whole argument, we feed in as the original argument, feed in as left argument to the inner function. And then we can use this as a train, a fork, just like we did in the key solution, as right argument. So now whenever we want to have the mask, which we called n here, we refer to that as the right argument. And whenever we want the original data, we refer to that as the left argument. And this space isn't needed either. So we can write it like that. And so on and so on. We could move the bits and pieces around, but these are just some possibilities of how this could be written. So we can write this whole thing as a nice fork that uses a defen, a lambda, inside as the middle tine. Thank you for watching.